Okay, this is exam 4 from fall 23. I start with this bar has a certain mass and length, and it's stationary and have three forces. First, we want to find out what is the net torque on the bar, and that's part A. I have three forces. This force, I'll call it causing torque 1, and notice that it causes a clockwise torque, so it'll be negative. This torque has zero torque, so I'm just going to label it as torque equals 0. The reason it's 0 is because it's acting at the axis of rotation. And then this torque, I'll call it torque 2, and it is causing the bar to go in a counterclockwise fashion, so it's positive. So I have negative torque 1 plus torque 2. That's going to be negative of 10 newtons times the distance to the axis of rotation, which is 2 meters, plus 10 newtons, that's this force, times the distance, which is also 2 meters, times sine of 30. Right, so that gives me equal to negative 20 plus 10, or negative 10 Newton meters, and because it's negative, it's clockwise. Now for part B, I want to know what is the angular speed, the bar after 3 seconds. There are several things we need to do. First, we need to find the moment of inertia. This is a bar, so it's 1/12 mv squared. That's 1/12 of the mass, which is 3 kilograms, times the length, which is 4 meters squared. 1/12 of 3 times 16, that's 48. That's 4 kilogram meters squared. So find the moment of inertia, and then I say that the torque is equal to I times alpha. And so alpha, the angular acceleration, is torque over I. That's going to be 10 Newton meters divided by 4. 10 over 4, that's 5 over 2. That's 2.5 radians per second squared. And then the final part is to find the angular speed. That omega is equal to omega naught plus alpha t. We'll assume that it's initially at rest. And so it's going to be 2.5 radians per second squared times the time, which is 3 seconds. That's 7.5 radians per second. So negative 10 Newton meters clockwise and 7.5 radians per second. Have a disk with a radius of 2 meters and 4 kilograms rotating, angular speed of 3 radians per second. I want to know the angular momentum of the disk, and so for part A, I first have to find the moment of inertia of that disk, which is going to be 1/2 mr squared. That's for a cylinder. That's 1/2 of the mass, which is 4, times 2 meters squared. That's 2 times 4, that's 8 kilogram meters squared. And then to find the angular momentum, that's just I times omega. I'm just going to assume that I want to know the magnitude of it. The direction of the momentum is different than plus or minus. We won't really talk about that. But anyway, I have 8 kilogram meters squared times omega, which is 3 radians per second. So that's 24 kilogram meters squared per second. So that's the answer for part A, is 24. And then you put this bar onto the disk, and it starts spinning along with the disk. They come together and start spinning at the same rate. And I want to know what is the speed of the disk after I place that bar. So I say Li is equal to Lf. Li is equal to 24. And so that's going to equal to the final angular momentum, which is going to be I of the disk plus I of the bar times this final angular speed. So I need to figure out what is the moment of inertia of the bar. Oops, sorry. The moment of inertia of the bar is 1/12 mv squared. That's 1/12. The mass of the bar is 3 kilograms, 4 kilogram meters squared, or excuse me, 4, not just 4 meters. Sorry about this. So the this distance is 2 meters. That means that this distance is 4 meters, and that's given there, the mass. So I have the mass times the length. The length is squared. That's 1/12 of 40. 1/12 of 3 times 16 squared, that's 1/12 48, or 4 kilogram meters squared. So I have then, coming back up here, I have 24 equals I of the disk, which we've already found to be 8, plus I of the bar, which is now 4, times omega final. And then when I solve that for omega final, I find that omega final is 24 over 12, or 2 revolutions per second. So that is omega F. All right. Number 3, I have water flowing in a pipe. It's 6 meters per second here, and it has an area of 3 meters squared, but then it goes down to 1 square meter, and I want to know what is this new speed. Well, I know it gets skinnier, so it has to go faster, and it gets skinnier by a factor of 3. It gets smaller by a factor of 3, so I know that the speed is actually going to go up by a factor of 3. So I could just say it's 18. What's going on in my head there is I'm using the continuity equation, A1 V1 equals A2 V2. That is 3 meters squared times 6 meters per second equals 1 meter squared times V2. That's 18 divided by 1. So V2 is equal to 18 meters per second, which is what I thought. It's going to go up by a factor of 3. Now I want to know the pressure in the narrow section. So this is where I need to use Bernoulli's principle. That is that rho GH plus 1/2 rho V squared plus the pressure, that these are constant. So all of this on one side, I could put ones on everything, are equal to, by the way, recognize that the height of the fluid doesn't change. So what I'm going to do is I'm just going to get rid of this term, and I'm not going to write the term on the right-hand side because it's going to be the same. So is equal to 1/2 rho V2 squared plus P2. Okay, so now I want to find out what is P2. So I have 1/2 of rho, this is water, so rho is 1,000, times V1, that was 6 meters per second, squared, plus P1, that's 50 kilopascals, or 50,000 pascals, is equal to 1/2 of 1,000 times 18 squared, plus P2. And then I want to solve that for P2. It's 500 times 36. 18,000. Was that an 8 there? No, an 18. 500 times 18 squared. $162,000 plus this new pressure, P2. I can solve that for P2. Okay, so sorry, I had to pause there for a second. I have a mistake here, so I'm going to, on your test, you'll have it in this version. Let me show you what happens. The thing is, when the fluid goes faster here, when the velocity goes up, the pressure drops. And so the pressure is dropping so much that it's going negative, and that's not physical. So what I'm going to do is, instead of having 50 kilopascals, I'm just going to make this 500 kilopascals. So instead of this being 50,000, it's going to be 500,000 pascals, 500,000 pascals, and then so P2 is going to be 518,000 pascals minus 162,000 pascals, which is going to be equal to 356,000 pascals, or 300 pascals. Oh, not a very realistic number. Sorry about that. I'll fix that. I might change it, but the way that you work it will be the same as that. Okay. All right. Yeah, that's it. Manometer is used to measure the pressure of a gas. This manometer is filled with liquid mercury, and the height of that column is 92 millimeters. First of all, I'll just ask, where's the pressure bigger? Is the pressure bigger in the argon gas, or is it bigger in the atmospheric pressure? Well, because this level of the argon is lower, then the argon gas is at a higher pressure. So the answer here is that the argon has a higher pressure. And the reason is because, you might have said this in a variety of ways, but because the level of the mercury is lower on that side, or something similar to that. Okay, just describing that because the level here is lower than it is here, then we know that that pressure on the left side is greater. And then B, I want to know what is the pressure of that argon gas. So I know that P is equal to P naught plus rho GH, and this would be my P, my unknown, and this is my known pressure. So now, should this be plus or minus? And since P I know is bigger, then I'm going to drop them negative. It has to be plus, and so that's going to be equal to 100,000 pascals. Plus sorry, folks. Hold on. Using a different computer than I usually use. Okay. Plus the density, which is 13,600. Times G, which is 10, times the height, which is 92 millimeters, and that's going to be 0.092 meters. When I calculate that, I get 100,000 plus 13,600 times 10 times 0.092. We get 112,000 pascals. Okay, I'm going to let my computer pause here for a second. I don't know what's up. Okay, a drum major carries a mace that is 2 meters long and has a mass of 3 kilograms. Spins the mace about the mace's midpoint, and it goes up in the air spinning. I want to know the energy. So here the total energy would be equal to the potential energy plus the rotational kinetic energy. All right, so that's going to be mgh plus 1/2 I omega squared. Let's determine the moment of inertia. I don't tell you that, but I do tell you it's 2 meters long. That's B, and it has a mass of 3 kilograms. So that's 1/12 of 3 times 2 squared. That's 3 times 4. So it's just 1. So I have 3 kilograms. That's the mass times 10 meters per second squared. Gravity times the height. It goes up to a height of 5 meters plus 1/2 of this 1 kilogram meter squared times omega, which is 4 radians per second, omega squared. So that's 30 times 5, 150 plus 1 half 16 is 8. It's 158 or 160 joules. So that's C. Figure skater spins with her arms extended. When she pulls in her arms, she reduces her rotational inertia and spins faster. Because remember, L is equal to I omega. So if this goes down, that's going to go up by the same amount. What about a rotational kinetic energy? Is it going to be larger, smaller, or the same? Well, the rotational kinetic energy is 1 half I omega squared. So if this goes down and then this goes up, but by the same amount, so say for imagine that this goes down by a factor of a half and that goes up by a factor of 2. And then if we think about our energy, then that would go down by a half and this would go up by 2, but notice that it's squared, so the rotational kinetic energy would be twice as big. And so that's the answer, that it's larger, and it's because she is rotating faster, and that this angular velocity is a squared term, and so it's more heavily dependent on that. All right, this object can rotate in the plane of the page. Rank them. Looks like I'm going from largest to smallest. Commented that this is my biggest moment of inertia because it's so far from all the mass, so I can get rid of any that don't have it, so I can get rid of those two. And I'm also commented that this is my smallest, but that doesn't help me any. So now I need to determine which is bigger, B or A. Okay, well, let's think about the distance to the mass, and whichever has a greater distance to the furthest mass, then that will, to the furthest point, then that will have the biggest moment of inertia because it has more mass out at a bigger moment arm or radius. And so how does this distance compare to this distance? Well, B is a further distance, so B has a bigger moment of inertia, and so IB is bigger than IA. Disk. Okay. Oh, this is similar to what we had in the free response. Oh gosh. Well, that's okay. I want to know what is the total moment of inertia here. So I have a disk. Is it this similar to what we had? Yeah, but different number. That's okay. We'll just let it slide. So here I want to know the total moment of inertia. I'm going to add those two together. I have the disk, which is flat cylinder, 1 half of the mass, which is 4, right there, times the radius, which is 2. So that's 2 squared. 2 times 4, that's 8 kilogram meters squared. And then the bar, the bar is 1/12 mv squared. That's 1/12 of 3 times 4 squared. That's 3 times 16, 48, so that's 4. And so that is 12 kilogram meters squared. I think that's exactly like the free response. Let's just double check. It is. I'm probably going to replace that with a different question, okay? But the answer here should have been C for number 4. But again, I'm probably going to replace it. All right, a potter's wheel is spinning at 3 revolutions per second. The wheel has a moment of inertia of 0.1. And then the potter throws on this lump of clay on the edge of the wheel. What is the new speed of the wheel? So Li is equal to Lf. The initial moment, the initial angular momentum is I initial, omega initial, and I initial here is just the wheel. So it's 1 half m r squared, which is 1 half of the, actually no, I tell you what it is, so it's 0.1. So I have 0.1 times omega, which is 3 revolutions per second. And now this is going to equal to, draw a picture here, I have this disk, it's sitting around there, and then he throws this lump of clay onto it. And that lump of clay, just the clay itself, has a moment of inertia equal to mr squared. And so the adding on of what we do is we have this 1 kilogram at a radius of 0.5 meters squared, that's equal to 0.25. So I've increased my moment of inertia from 0.1 to 0.1 plus 0.25, which is times omega final. And if I solve that for omega final, I get omega final equals 0.9, 0.3 over 0.35, which is almost 1. What is the angular acceleration of this bar? Again, similar to what we did in the in the free response. Ooh, I might change this also, y'all, just so it's not so similar. Recognize this one doesn't have any torque. This one is a negative torque. I'll call it torque 1. And this is a positive torque. I'll call that torque 2. And so the net torque is going to be negative torque 1. That's negative 10 times 1 meter. 10 newtons times 1 meter. Plus torque 2, which is 5 newtons, also times 1 meter, times sine of 30. That's negative 10 minus 2 plus 2.5, which is negative 7.5 Newton meters. Then I need to find the moment of inertia, 1/12 mv squared. 3 times 2 squared. That's equal to 1. And then so alpha is going to be torque over I, 7.5 divided by 1, which is 7.5. And because it's negative, it is clockwise. All right. Rank these torques from greatest to least. Okay, the one that's going to be greatest is going to be A, because I have that force. And notice all the forces are the same in magnitude. I say that right there, and they look to be the same length too. So A is going to be the biggest. That gets rid of that one. Also recognize that A is not equal to B, so I can get rid of that one. This one has 0 torque, and this one also has 0 torque. That means C is equal to D. Now, next I want to think which one gives me a bigger torque. That doesn't help me, by the way. Does this one or this one? This is a pretty shallow angle, so it's not going to give you hardly any torque at all. So it's going to be A followed by B followed by E followed by C and D, which have 0 torque. This is a SI unit for angular momentum. That's I. Omega is angular momentum. I is kilogram meter squared. Remember, mr squared. Omega is radians per second. So it's kilogram meter squared per second. And that radians is really just sort of like a placeholder. Rectangular boat has these dimensions. What weight can it hold? Well, the weight will be equal to the buoyant force, and if you exceed the buoyant force, then the boat's going to sink. So the buoyant is equal to the density of the fluid, which is water in this case, the volume of the object, times g. That's going to be 1,000 times the volume, which is 3 times 2 times 0.5, that's 6.5, that's 3 meters cubed, times 10, so that's 10,000, 30,000 newtons. Pascal's principle, just need to know what Pascal's principle is, a change in pressure at any one point. And then likewise, the same options, but for Archimedes' principle, the buoyant force is equal to the weight of the displaced fluid. Pipe has a cross-sectional area of 2 meters squared. It opens up to an area of 4 meters squared. I always like to draw pictures for these. Helps me to think about it. So I know that the velocity in this section is going to be bigger than the velocity in that section. So I have a big velocity, small velocity. And remember Bernoulli's principle, I want to know about the pressure of the fluid as it goes from the small to the big pipe. As the velocity goes up, the pressure goes down. So I have a small pressure here and a big pressure here. That's not intuitive. Like if you're just looking at it, you would probably think that this would be the small pressure, but it's not. The pressure is going to increase. So B is 12. Okay, so similar, I have a pipe going from 1 square meter to 0.3 square meters. Getting 1/3 is small, that means the velocity is going to go up by a factor of 3. So whereas it was 3 meters per second, it's now 9 meters per second. You had a very similar, or this was part of your free response where I say A1 V1 equals A2 V2. I'll leave you to do that on your own. What is this material? Has a mass of 220 kilograms and a volume of 0.021 meters cubed. I just find its density. I can measure its mass and its volume, measure the volume by displacement perhaps, and then if I can find its density, I can check against my table of densities and determine which one it is. So that's 220 divided by 0.021. I get 10,476. And I have that's lead. I don't have that table right in front of me, but I do have the answer, so that's lead. Here, this is a hydraulic press. On this side, I have an area of 0.5 square meters, or square centimeters, it doesn't matter really. Over here, I have an area of 1 square centimeter. So my area is getting bigger. On this side, I put in a force of 80 newtons, and I want to know what is the force over here. What I do know is that the pressure on both sides is the same. That's 80 over 0.5 is going to be equal to the F on the right-hand side, the force on the right-hand side, divided by 1. So that's 160 newtons for number 15. What is the SI unit for pressure? That would be Pascal, or newtons per square meter. Other units do include the atmosphere, which is commonly used, but our PSI, or pounds per square inch, but those are not the SI units. The SI unit is the Pascal, which is equal to a newton per square meter. What is the pressure exerted? In this case, I have a 45 newton force on the edge of a chisel that has a small area of 0.5 square centimeters. That's going to be 45 newtons. Pressure is force over area divided by the area, 5 times 10 to the minus 5 square meters. Look, I went and did the conversion for you, and that is equal to 900,000 pascals. It's a pretty big pressure, 900,000 pascals. It's 9 atmospheres. What is the most abundant substance in the universe? That would be dark matter, somewhere on the order of 95% or so. And then here, a tungsten wire has a length of 2 meters and an area of 7.1 times 10 minus 6. I have a force of 1,960 newtons that just hangs on it, and I want to know what is the increase in length. So I say F over A is equal to the Young's modulus times delta L over L naught, and this is my original length. And then I solve that for L naught. When I do that, I get that L naught is equal to 1.6 times 10 to the minus 3. You have to look up this Young's modulus in your table. I don't have that right now, but just look it up on your table. It's on your equation sheet. And I get this in meters, which the answer is in millimeters. And then number 20, obviously the answer is D. All right, maybe a couple of changes between the actual exam and this video.